Okay, thank you. Okay. Apologize that my Russian colleagues could not come to the conference. Is it all right now? Okay. The basic ideas I'm talking about here are actually by Natan Eismont at the Space Research Institute in Moscow, and his colleague Irina Kovalenko. The two of them have done most of the work. I'm maybe something like less than 20% of me is in this presentation. The basic idea was actually to study for impacts, to defend against impacts by Apophis or by other near-Earth asteroids. The basic scheme was to launch a spacecraft and attach it to a near-Earth asteroid, an asteroid which naturally comes fairly close to the Earth, and then move the asteroid, give it a small delta V so that it actually passes very close to the Earth and does an Earth swing by then. And you change the B-plane point with the thrusters so that the spacecraft, the asteroid's orbit has changed to impact a hazardous asteroid, which is coming towards the Earth. And the idea is the asteroid, it would be something like a 6-meter asteroid or so, or would be, if it's a small asteroid, you'd use the whole asteroid, or you would just pick a boulder off of a larger one of the right size that you could handle. But this then increases, so it's a kinetic impact idea, but you're increasing the mass of your essentially your spacecraft by a factor of more than 2 orders of magnitude. So previous work has already been done in this direction. Most notably the asteroid redirect mission from about 2012 to 2017 did quite a detailed study, and that would do the same thing that I just discussed, except instead of changing a B-plane point, it would actually put the boulder in orbit around the moon. Similarly, in 2015, Marcus and Barbie, Sloan and Ortiz, developed what they called the Billards concept to do the same thing, but to move a small asteroid or a boulder into the path of another asteroid. And they had a couple of specific asteroids, not using an Earth swing by, but just taking a small asteroid that's naturally passed near another one. And we've done previous work on this, the technique that I showed in the previous slides back in 2012 and 2014. We've had a couple of papers on this. This just shows the ORX has shown that Bennu is just littered with boulders, so there's no shortage of boulders of the right size that we could select. I think from any of the asteroids that have been studied, all have lots of boulders. Hayabusa with Ryugu and Itokawa too. We can always find what we need, and then the idea then is, as I said in the first slide, or the second slide, was to change the B-plane point and do an Earth swing by. And this just shows that you can get a large change in the direction of the relative velocity vector. So you can make a very large change in the orbit of your projectile asteroid. And you can change it by this angle alpha here, which is shown in the next slide, right? And down at the bottom there. So this just shows on a sphere how you can get quite wide range of change. And this just shows gravity assist maneuvers depending upon different perigee distances. So you have variation. You vary the perigee distance and the angle, and that gives you the control. So the next slides just show some of that. And I showed this, the bend angle that you can get depends upon the radius of your flyby and the velocity and relative velocity and the gravitational parameter of the Earth. And so R can only go to some lowest value, which we select as 6,700 kilometers. But that can give you quite a wide range. Then to navigate the asteroid projectile, we would propose to fly a couple of sub-satellites along with the asteroid, and if possible, also put a transponders or retroflectors on the target asteroid as well as the projectile asteroid, and then measure all these distances extremely accurately. And then, so that would be the idea of the guidance involved. I go to the next slide. So the idea, though, is not just to, I mean, the first slide just showed deflecting an asteroid, a random asteroid that was passed near the Earth directly into a threatening asteroid. But another idea is to capture the asteroid into a resonance orbit about the Earth, so that essentially you aim it to a keyhole so that it comes back to the Earth again on a one-year orbit. So we looked at that with the current catalog. This work was done in 2014, and we have a lot more asteroids in the catalog now, and we're going to get a lot more in the future. This just shows the idea of the resonance orbit, then, depending upon too high. You can change, as I said, both the distance, the alpha angle and the rotation angle gamma to get a variety of orbits that are all period 1 year. Essentially, you can vary the inclination and the eccentricity. They vary by these formula here. The beta angle is related to the alpha angle, and the gamma is the other out of plane parameter. So this just shows 6 different resonant orbits for the asteroid 2012 VE77, showing how they all intersect the Earth at the one point here, but they're all very different orbits depending upon their eccentricity and inclination. And this just shows the very wide range of eccentricities and inclinations that you can get up to 30-degree inclination. This idea will work for asteroids that, for comets that have a very large inclination. This technique won't work, but or at least is less effective. But we've found 12 different asteroids that at different times of the year that we could put into Earth resonant orbits like this. One of them is Apophis, and this just shows the years in which, in the months and the dates when the asteroids would be there. And in one resonant orbit, if you have a resonant orbit with the zero eccentricity, the orbit will intersect the Earth's orbit twice on opposite sides, and then you can essentially do kind of a backflip maneuver and switch it to the other node. So there's quite a bit of flexibility here. Now, this is all far in the future. It's not something that we could do for PDC 2019 because we don't have anything up there yet. And we'd hope to do a demonstration experiment using the ARM technology plus something like billiards or something, to test something this out, you want to test this out on some benign asteroid before you would actually try to set up a system like this. So, this might be 30, 40 years in the future before we would even seriously consider such a thing. But the threat from long period comets is serious, and it just can't be addressed with our other standard techniques. I think you really have to have something in place beforehand to be able to take care of it. And this is a proposal that might do that. Anyway, well, this just talks about the what I've already said before. So the operations can be done with further gravity assist in order to reach optimum parameters for your orbit. This just shows the parameters for these asteroids that we have studied already. And this and the table of gravity assist maneuver parameters are in our paper, so which will be on the planetary disk. This just shows POT4 resonant asteroids, which could be diverted then to intercept a comet coming in from the right here. So you'd have not just one chance, but you would have maybe a couple of 2 or 3 chances depending upon the particular orbit parameters and what you can get with the particular asteroids that you've set up as projectiles. And so anyway, we found then more than 10 asteroids were found which can be delivered to an Earth 1-year resonance orbit by applying a delta V of less than 20 meters per second. Of course, 20 meters per second is a huge amount for moving even a 6-meter asteroid, but with a much larger catalog that we're going to have soon, that 20 meters per second could be down to 2 or 3 meters per second, could be much less, to something that we might be able to handle. And also, we'll have more and more robust propulsion technology in the future to be able to do such things. And so then I just concluded with the constellation might be constructed that allow with enough time that as long as you have 2 years of warning or something, you might be able to deflect something into a threatening object coming towards the Earth. So I think with that, I want to close. Thank you.
Thank you very much. Thank you. Very cool idea. One question, very quick one.
Joe Newth, NASA Goddard. It looks like it's cutting it awful close. If you miss, we're dead.
That's right. That's right. It's this would be a last resort, but if you don't have anything, then for sure you're dead.
There, I completely agree with you. The other question is, have you looked at all into what the fragmentation would be, whether or not you would? Okay.
No, we haven't looked into any of that. There's just tons of things of studies that need to be done to, for, as I said, this is like 30 years in the future or something. But we're starting to look in these things. The DART mission is. We'll first start learning some of these things about properties of asteroids and what you can really do. What would happen if you hit a rubble pile with a 6-meter boulder, going with a relative velocity of 10 kilometers per second or something.